Okay, so good morning, everyone. We're here with Tania Rayan Corporation, and I'm Tania, and this is my partner Rayan, and we're going to present to you the RT processor today. So let's get started. The agenda. For today, we will be talking about the origin name of the company, our MIPS overview, MIPS architectures, our data types, our baseline instructions, our interrupt, what went wrong, future enhancements, and our final questions. Okay, so the origin of the company. So as you can see, we use the first three letters of our name, which is Tan and Ray, and we just combined them and made it our name. So for the processor's name, we took the first letter of our name, R and T, but we made it a little special and put RT. Okay, so MIPS overview. So MIPS stands for million instructions per second, and it was first introduced in 1981, and we have a couple of revisions, which some of the current revisions include the MIPS 32, MIPS 64, and some of our MIPS processors are used in embedded systems applications like routers, residential gateways, and game consoles. So our MIPS architecture. MIPS is a reduced instruction set computer. It's 32 by 32 bits. It's byte addressable. The memory is organized by big endian format, which means that the first bit, the most significant bit is stored into the lower address here, as you can see here, and so forth, all the way until we're done. MIPS has three baseline instruction formats, which is the R type, the I type, and the J type. And if we want to use our enhancement instructions, we have to use 1F as our opcode. So Harvard architecture. Our Harvard architecture, as you can see here, consists of the CPU, the instruction memory, and data memory. And in our case, we have our I/O memory. And Harvard architecture is basically a computer architecture in which the instructions and the data address are separate. As you can see here, we have two. And they're connected by an address bus and a data bus. And this enables us to be able to write into it, memory and read from memory.
How big is your data bus?
Hmm?
How big is your data bus?
It's 32.
Oh, you have to change that slide.
Yeah, that's the difference. Okay, so our data types. We have two, which is our signed 32-bit integer and our unsigned 32-bit integer. Our status flags, we have 5, negative, overflow, carry, and 0. And our interrupt enable flag. These instructions are the only ones that update the overflow, carry, and 0 flag. And any other arithmetic or logical operation update the other flags. So addressing modes. We have 3 addressing modes, as you can see here. The first one is our immediate addressing mode, which means that the operand itself is part of the instruction as an immediate value. As you can see here, our immediate value is 3, and we're adding it to the content of S4 and storing it back into T5. So for our immediate values for our I instructions, it's only 16 bits, and for our J type instructions, our immediate value is up to 26 bits. So for the register direct mode, the instruction uses the value in the register specified by the address. So, and this has to be known by compile time, so the contents of these registers have to be already stored in there before you actually add them. So here we have the S1 plus S2 is back, you put it back into T1. So for our register indirect, this specified registers holding the address of the operand. So this mode is for our load word operation here, which means that we're taking the contents of S1, whatever is inside, and we're adding it with 0, and then we're loading it back into our T1 register. This is how we load our values into the registers we will be using. Okay, so next up is instruction set and formats. So our first instruction format is our R type, which we have here. We have, as you can see, we have 20 instructions in the R type. So we have our shift, our jumps, our move high and low. We have the multiply, divide, add, our subtracts, add or, our set less, our break, and our set high. These are our R type instructions. So for the R instructions, our format is consisting of the 6 bits of the opcode, 5 bits of the RS, 5 bits are the RT, and 5 bits for our destination register. Our shift amount, which is only used when we shift, and 6 bits of the function select. So our syntax here we use two source registers, RS and RT. We combine these, we're adding them, and then we're putting back into our destination register, which is RD. As you can see here, in our examples, we're adding T0 plus T1 and then putting it back into T1 using our art type.
Okay, for our media type instruction format, we have 13 instructions which are I-type, including the branch of equal, branch of not equal, add immediate, set less than immediate, and immediate, load upper immediate, load word, and store word. So the immediate type is used for immediate and register indirect operations. The format is as follows. We have a 6-bit opcode, a 5-bit field for RS, and a 5-bit field for RT. RS is the source register, and RT is the destination register. We have a 16-bit offset used as the immediate value. So in our example shown, we have an add immediate, where we add RS with the immediate value and store it into RT. For our jump type instruction format, we have 3 instructions which follow the J type, including the unconditional jump, the jump in link, and the jump register. The unconditional jump has a 6-bit opcode and a 26-bit target address. The syntax is as follows: jump 26 to a 26-bit address or immediate value. The RTL operation is as follows. We have PC getting loaded in with a concatenation of PC plus 4 times the most significant bits of the instruction register, because each word in memory is 32 bits, so 4 times a byte equals 32 bits. And the immediate value is shifted left twice, because the immediate value is a 26-bit value, and we want it to be 28 bits to equal the total 32 bits width of the PC register.
Okay, so for our top level instantiates the MCU, which is a MIPS control unit, our instruction unit, our integer data path, our data memory, and our I/O memory. In this case, our MCU contains the control words for each instruction, which this helps us pick out whatever instruction we need to do, which is either subtract, add, or whatever we're going to do. And all the control words are contained into the MCU. Okay, so for our integer data path, it instantiates the LEU and the register file. As you can see here, we also have 2 registers, which are only used when we are doing a divide or a multiply. This helps us contain our 64-bit answer. And in the case of divide, one of them is stored, the remainder is stored into one of these registers, and then at the high register we store the quotient.
So our instruction unit instantiates the program counter, the instruction memory, and the instruction register, and it includes the assign, extend, 16 operation. What this does is it takes in 16 bits and it shifts them left to equal 32 bits output for the offset for load and store words. The PC mux is used to select the PC or the jump address or the branch address, depending on the instruction. The data memory is used to, we use the data memory to read and write for load and store. Writing is synchronous while reading is asynchronous. There's 3 control signals: a chip select, write enable, a read enable. There's a 32-bit address port and 32-bit data port, which are clock and reset. The I/O memory is an exact block copy of the data memory, except for that it generates an interrupt request, and it takes in an interrupt acknowledge once the interrupt service routine or subroutine is completed by the CPU.
Okay, so interrupts. For this case, our first step was to send out the interrupt request. Once that was sent out, the interrupt service routine begins, and then the process saves the state of the machine by pushing the PC flag into the register and onto the stack. flag registers onto the stack. So then we stored the interrupt vector in the last data memory, which is 3FC. And then once that is done, our interrupt service routine is done. The return from interrupt occurs, so it sets the flags, and then the flag register and the PC is pushed off the stack in reverse order. And once this is done, we hit the return from interrupt. It's going to go back into whatever instruction it was interrupt, and it's going to keep going from there. Okay, so our problem. One of our biggest problems for this project was to get our interrupts to work. We had quite of mistakes, and we couldn't get them to work at the end. So first, our interrupt request was never sent out. Once we figured out that it didn't take us long to figure that out, but we found out that the mistake was in the our SETI instruction. Once we fixed that, we came into the problem that we had that our positive edge interact acknowledge. This line we did not have, so we were missing. Therefore, none of our our register content was printing out. So we had a big issue there. We had to go check into the waveforms to see what was happening. So once that was set, we put that in. We were able to get our printout. But the thing is that we weren't printing out our I/O memory, so it wasn't working. We weren't able to fix this when we turned in the project. But while I was working on trying to fix this, my partner was working on our enhancements, which we're talking about, or I'm going to talk about. So our first enhancement would be the divide by zero flag, and the second one was the conditional move if zero, which Ryan will be explaining next.
So the divide by zero flag was a fairly easy implementation. The code was implemented in the division module, which is located inside the ALU. So we cast the two inputs as integers, and we check to see if the divisor is not equal to 0. And if it's not equal to 0, we go on with the division operation, and we set the flag equal to 0. Else, we set the flag high, and we refrain from dividing. The conditional move if 0, unfortunately, we did not get to implement completely, as we didn't have the time to actually write the instruction memory to execute the instruction. But just to get a better understanding of what the instruction is and how it is compiled, this is the high-level code. So if A is equal to 0, store T into S, and the straightforward compilation of that would be to branch if R1 is not equal to 0, to label, skipping the move instruction, else if, so R1 is A in this case, else if R1 is equal to 0, move T into S or R3 into R21. So the reason why we want to continue with implementing this instruction is because many modern processors today, including the MIPS, actually use a conditional move to optimize compilation of code. So the assembly syntax you see here is C move Z, R2, R3, R1, basically means if R1 is equal to 0, then move R3 into R2. It does follow an R-type format. A possible implementation that we brainstormed and came up with is, in the first state, to pass RS into ALU out through the ALU. In this case, RS would be R1. So we're planning to check to see if RS is equal to 0. So in the second state, we do that by checking the present state of the 0 flag. If that's set to 1, then we carry on with the move instruction. But in our case, we use an add with R0. In this case, RT would be R0. RS would be R3. So if present state is equal to 1, we continue with the move. And then the third state, we'll write back ALU. The destination register, which would be R2 in this case.
Okay, so for our future enhancement, continuing on, we would have liked to pipeline, which we know that it's set to pipeline, but we didn't have enough time to get to that, but that's going to be for our future enhancements. And we know that we can change some of the muxes and add a forwarding unit to make the pipeline happen.
Another enhancement we want to make is to actually give the ALU the capability to perform 64-bit operations, which would mean each operand 64 bits. which will require the S and T port to be 64 bits width instead of 32.
So any final questions you guys have?
Can you go back to your problem slide? So that's the solution you said?
No, we didn't have a solution for it. Our I/O memory is not printing out correctly.
Yeah, but so you see anything wrong with that? Like waiting for the positive edge before you set the interrupt? Is that the way you have it?
Yes. Okay, so at the beginning, we didn't have this line. For whatever reason, it was in our previous modules, but when we got to 13 and 14, trying to fix it, we might have had deleted that line because I found it in our previous modules. So when I look back into it, this line wasn't there. So that's why we weren't getting any printout. So the printout we have, our register module has the right content in it, but we don't have a printout for our I/O memory.
But is that how you're currently doing the
Interrupt?
interface? Yeah, the handshake.
Yes, that happens in our I/O
Because I
module.
think the interrupt request comes first. That's the first edge, not the interrupt acknowledge as far as the process.
Oh, we kind of named them backwards at the beginning. Yeah, I know. This is supposed to be interrupt request, and this is supposed to be here.
No.
Yeah, because the interrupt request would be our input, right? And then this is our output. Well, for our
Your interrupt
I/O
request is your output from this. This is, where was this code?
memory. In our I/O memory.
Yeah, so interrupt request is the output there, not the input. So you'd
Okay.
want to set that first and then wait for the acknowledge
Yes.
second, and then turn it off.
So, yeah, basically this is wrong, and we're
Okay.
trying to fix it.
Yeah. I think
but
if you just pull out the app pause edge interrupt acknowledge, that would be the proper protocol.
we did take it off, but it doesn't print. Like our data doesn't print. The registers, we check the waveforms and they're right.
Yeah.
But for some reason, we're not printing out our content.
Yeah, so that's another problem.
Yeah, that's another
Yeah,
problem that
okay.
we have.
Yeah,
Any other questions?
very well organized, good job. Yeah, very well prepared, good job.